All right, let's dive right in. Deep, deep beneath our feet, there's this colossal engine made of molten rock, and it's constantly churning away, powering the very ground we stand on. But what if that engine isn't the steady, predictable machine we've always imagined? What if it's something wilder?
So, we're going to start with a concept that probably sounds familiar from science class: plate tectonics. That slow, epic dance of the continents that's driven by these incredible forces deep inside our planet. And the way we usually picture it is pretty simple, right? It's almost like a giant conveyor belt. Hot stuff rises from the core, it cools off near the surface, and then it sinks back down in this really steady, reliable loop. And that's what pushes the continents around. It feels orderly, almost mechanical. But here's the kicker. What if that whole picture is wrong? What if the massive currents in the Earth's mantle aren't this smooth, repeating cycle at all? What if, at their very core, they're fundamentally unpredictable, complex, and, well, chaotic? To really understand the chaos happening inside the Earth, we first have to look up at the sky. This whole story, kind of surprisingly, starts with a meteorologist named Edward Lorenz, who was just trying to predict the weather. Now, the really important word on this slide is deterministic. This isn't just random chance we're talking about. Chaos theory is all about systems where even if you know the exact rules, and I mean exact rules, the outcome is still impossible to predict long term. Why? Because the tiniest, most microscopic difference at the start can lead to wildly different results down the line. So what Lorenz did was he took the super complicated math that describes convection, which is the same process happening in the Earth's mantle, and he boiled it all down to just three simple equations. He was totally expecting to see the system just settle into a nice, predictable loop. He was really, really wrong. So, instead of a simple loop, the system he modeled traced out this path that literally never repeated itself, ever. But, and this is the cool part, it was always confined to this beautiful butterfly-shaped pattern. This is what's called a strange attractor. The system is sort of attracted to this general shape, but its exact path through it is always unique, always unpredictable. And this was our first real glimpse of what deterministic chaos looked like. So naturally, this leads to the huge question. If the simple equations for convection are chaotic, does that mean the Earth's mantle is too? I mean, scientists were buzzing. But when they tried to apply Lorenz's model directly to our planet, they hit a massive wall. Okay, so here was the problem. The Earth's mantle is incredibly viscous. We're talking thick like cold honey times a billion. In physics, this is described as having a nearly infinite Prandtl number. When the scientists plugged that detail into Lorenz's simple three-equation model, all that beautiful chaos just vanished. The model just settled into a boring, stable, predictable flow. And for a while there, it really seemed like the answer might be yes. Was this whole chaos connection just a fascinating little detour, but ultimately irrelevant for geophysics? Was the Earth's engine just a simple conveyor belt like we thought all along? And then came the breakthrough, which this slide shows so perfectly. Scientists realized that Lorenz's model was a huge oversimplification. I mean, the mantle isn't governed by just three little variables. So when they built more complex models with 12 or even 40 equations, the chaos came roaring back, even with the mantle's crazy high viscosity. The problem wasn't the planet, it was that our first model was just way too simple. So, okay, we've confirmed it. The engine is chaotic. But so what? Why does that even matter? Well, it turns out this isn't just some abstract mathing. It has these profound consequences for the very structure of our planet. And that's a fair question, right? Who cares if the flow is messy or smooth? Well, it turns out to be the difference between a planet that is really well mixed and dynamic and one that's just kind of layered and stagnant. Think about it like this. You're stirring cream into your coffee. If you just move the spoon in a simple, perfect circle, you're going to get streaks, right? It doesn't mix very well. But if you do a chaotic stir, up, down, all over the place, it blends completely. That is what chaotic convection does inside the Earth. It's a ridiculously efficient mixing spoon. And you can actually see what that mixing looks like in action. In these models, scientists tracked a little blob of particles. At first, they're all clumped together. But really quickly, the chaotic motion just grabs them, stretches them out into a long filament, folds it, stretches it again, and keeps doing that until those particles are spread pretty much evenly through the entire system. And the scale of this whole thing is just, it's mind-boggling. This chaotic stirring is so powerful that it can take a 10-kilometer thick slab of crust that gets sucked down into the mantle and, over about 500 million years, stretch it into these thin little ribbons just centimeters thick. This is literally the process that creates what geologists call a marble cake mantle. Amazing. So, how do we actually know all this? I mean, you can't just drop a camera down there. The full equations are way too complex to solve directly, so scientists have come up with this amazing toolkit of approximations to get to the truth. They use these really clever tricks, like instead of trying to calculate everything at once, one method, boundary layer theory, lets them just focus on the thin, unstable layers at the top and bottom of the mantle, because that's where most of the interesting action, like new plumes being born, really happens. Each one of these methods gives us a different piece of the puzzle, letting us build this incredible picture of a super complex system. So, what's the big takeaway here? Chaos isn't some flaw or messy error in the system. No, it is the essential feature. It's what allows our planet to efficiently recycle its crust, to mix its interior, and to drive the plate tectonics that have shaped our entire world. The engine is messy, and that's precisely why it works so well. And that leaves us with one last thought. We started this journey trying to predict the weather. Then we dove into the Earth's core. But these exact same principles of deterministic chaos are absolutely everywhere. It really makes you wonder, what other complex things that we see every day are just the surface of some beautiful, hidden, chaotic dance going on underneath?